Alright class, I'm going to record the last section of last week's lecture. So let's let's pick up where we left off. So the last time we talked about a 3-electrode sensor, and we talked about why you need 3 electrodes. So let me kind of back up here. If you recall from looking at the blood gas sensor, we said that we basically to convert to measure a chemical, you need 2 electrodes, such that you have such that you have a reaction at one of the electrodes that produces some electrons, which then you can capture at the other electrode. So let's talk about this one here. Just a review. You have the, if I can find my mouse here, you have the cathode. And at this point, for us, specifically the blood gas sensor, you have oxygen plus some water. When they combine with some electrons that are coming from the circuitry down here, will give you some hydroxyl molecules, which are OH minuses. Those then get pushed to the anode, and then this is where the reaction kind of happens for this specific sensor. So when this OH minus hits the anode, it reacts with silver chloride, which then captures the electron, and then it gets driven through the circuitry here to be measured. So in this case, you only need two electrons, but what it's not explicitly stated in this slide, really, I guess it is here, but that you have to be able to drive hydroxyl atoms between the cathode and the anode, you have to have a voltage difference here. That also creates a reaction at each of the electrodes, and it also drives current through, or I should say, between those electrodes. So you have to be able to, apply a constant voltage that will allow these reactions to happen. But in the process, you also have to measure current that is produced by those reactions. And so at the end of the day, it turns out that, being able to apply a voltage between 2 electrodes, but also simultaneously measuring current through those same 2 electrodes is pretty difficult. And the reason why is because when the current does flow through those 2 electrodes, it can change the voltage between them, which then is basically competing with the requirement to hold that voltage constant. And so to get around that, you basically introduce another electrode into your system, and that's where the 3-electrode system comes into play. So you're going to have what's called the working electrode, so it's WE, and it's basically the electrode at which the reaction that you're interested in happens. So in the case of, remember from the glucose sensor, that's where hydrogen peroxide is being broken down into electrons. Once that happens, you're going to have 2 electrodes here interacting with the working. The reference electrode is the electrode that you're going to keep to be your reference voltage, and the voltage between the working and the reference is going to be what's going to be constant. So you're going to keep that voltage between these 2 electrodes constant. That's what's going to drive ionic flow between the working and the other electrode. It's also going to allow the reaction that you want to happen at the working electrode. So that's working. Reference is, again, your reference electrode. The working electrode typically made of like platinum, silver, carbon, or gold, and the reference is should be very stable, and it's usually pretty small. And the reason why it's small physically and geometrically is because it has to have a really high resistance. Because remember, I just mentioned that you don't want any current to flow between the electrodes that are producing your constant voltage in your system. And so you want no current coming from the working and going to the reference. That's going to affect the constant nature of your voltage in your system. So this should be very small and should have a very high impedance, and typically, they are made to have really high impedance. The other electrode is called the counter electrode, and again, that's usually made of also platinum, carbon, or gold, and this one is the one where current should sink. So this one should have a very large surface area for current produced at the working electrode to then go to the counter and then be measured by some circuitry in your instrumentation. Alright, so the working and the reference allow you to keep a precise applied voltage, and the working and counter allow you to actually measure that current that's produced from that reaction. Okay, so let's talk about what instrumentation needs to be attached here to allow you to measure the current produced by these reactions, and also to apply a voltage between the working and the reference. Now, I don't want you to get lost in the details here, but remember that the whole reason for this is that we have to indirectly measure some chemicals in our biomedical sensor. And so this is going to allow us to do that, to apply a voltage and then basically pick the reaction we want to happen and then measure the current from that reaction. So here's the general principle. So now we're going to get into specifically what's attached in terms of instrumentation. So here's a bath of solution. This could also be like tissue in your body, and these electrodes are sitting in your tissue, for instance. And so you're going to have working and reference and working and counter electrodes. You're typically going to use some operational amplifiers to achieve constant voltage between working and reference, but also some form of op-amp configuration such that you can also measure between the working and the counter electrode current. Okay, so when you're using op-amps, what's important is that you don't sink any current into your instrumentation, with the exception of just the working to counter electrode current that you're supposed to be measuring from the reactions. So what that means is that your op-amp shouldn't have a low impedance at the inputs, so they should have high input impedance. And what that translates to is that you're going to have small bias currents going into your op-amp components. So you want to aim for like a picoamp or less, because the amount of amperage you produce for these reactions can be on the order of micro to nanoamps, and even for some really small reactions, even picoamps. You also don't want any amplifier offset. That's when one of your references say it's grounded. You don't want any voltage produced across the working that's not controlled by you, the engineer. So you want offset that's much lower than like 10 millivolts. You're going to be applying voltages across the working and reference that are on the order of a couple of volts, and even as low as a couple of hundred millivolts. So this needs to be also very small. Alright, so here's a very simple example of how you can basically connect some instrumentation electronics to your 3-electrode system. So this little circle represents your electrochemical cell. So this is like, again, pretend this is like some electrolytic solution. You have 3 electrodes, the counter, the reference, and the working. This is not a transistor, though it does behave like one, but it's not a transistor. So the way this works is you're going to use one amplifier to be your control amplifier. And again, this is just to apply a voltage, a constant voltage. From your op-amp rules in ECE501, you know that when you have negative feedback, a couple of things happen with your op-amp. And so how do I know I have negative feedback? Well, you have the inverting terminal connected to your reference, and you have the output connected to your counter. So where's the feedback? The feedback actually happens in the electrochemical cell. So the counter and the reference are both connected to the same nonlinear device, essentially, and so that constitutes negative feedback. So when you have that, you're going to have that the input of the non-inverting terminal is going to equal the input of the inverting terminal. So if you're applying at the non-inverting terminal negative E sub I, you're also going to be applying negative E sub I at the inverting terminal right here. Because the reference is sitting at negative EI, then the difference between the working electrode and the reference electrode when the working is grounded is going to be E sub I. So this is going to be, V cell is going to be E sub I. So this allows you to basically apply E sub I between the working and the reference electrode. and you're going to have some current that is then measured between the working and the counter electrode. Alright, so now this circuit just helps you to apply a constant voltage. Now you're probably wondering, like, why can't you just apply this right here with like some kind of power supply? So the reason is because this op amp actually gives you a high input impedance, so this thing doesn't draw much current. So if you were to put a power supply, there's no guarantee that the input impedance of the power supply won't sink any current from the electrochemical cell. So that's basically why. So this gives you that high input impedance between what you're applying from some voltage source and the reference electrode. Alright, so let's get a little more sophisticated. So if you wanted to improve the previous example, then you would put a buffer in between the reference and the control amplifier that basically increases the input impedance that the reference sees, because now you have the impedance of the non-inverting terminal of the voltage buffer plus also the input impedance of the control amplifier as well. If you do the math, which I encourage you to do, again, this is still having negative feedback because from this op amp here it goes back to the input. You can prove to yourself that V cell is still equal to E sub I for this configuration. And to work it out, to kind of help you out here a little bit, you ground the control amplifier non-inverting terminal. That then creates this to be 0 volt as well. If you do, Kirchhoff's current law at these nodes here, you're going to find that V cell is basically E sub I. Okay, so that's how you can find that. And this just improves the amount of current that is basically sucked into the reference electrode. Alright, you can also make the reference electrode very small compared to these other two electrodes, and then that will also effectively increase the impedance of this line. Okay, oops, sorry, I just dropped my microphone. Alright, so going back to this. Now if you actually want to measure current, I'm taking the previous control amplifier configuration and I'm going to then add some transimpedance amplifier. So again, applying a control amplifier, you can also put a buffer here if you wanted to. You can apply E sub I at the reference, and to actually measure current from working to counter, you can connect the working to this transimpedance amplifier. So this should have been covered in ECE240. The current going from working to counter is the current that's coming through this line right here. And because you have a op amp that has a high input impedance, no current goes into this op amp, so all of IF comes from RM. And so you can then measure a voltage at the transimpedance amplifier, which is proportional to RM and IF. Now notice here that the working is not physically connected to ground. It's virtually connected via this transimpedance amplifier. So virtually this is at 0 volts, even though it's not really at 0. Now the problem with this is that obviously these are real amplifiers, so they'll have an actual offset, and so this might not be totally 0 at this node right here, and so that can affect your reading as well. So that's just something to consider when you're actually using these devices. But this is how you combine the control amplifier to create a constant voltage across the reference and the working, but you're also able to then measure between the working and counter with the transimpedance. Okay. So I mentioned this earlier, that the most commonly used electrochemical cell that you'll ever see is in a glucose sensor. So this is the way they work. I actually do have one here in my office, but typically you have some casing, and then you have this 3 electrode system that's in here basically. So this picture here constitutes like skin, some interstitial fluid, and then the actual blood vessels, and you can see that glucose does go from the blood to your interstitial fluid, and there are some mathematics that relate how the concentration of glucose in your interstitial fluid is related to the actual sugar levels in your blood. So this sensor has 3 electrodes. It has the working, counter, and reference, and they're designed a specific way such that the reference is very small, the counter has very large surface area, and the working also does as well. So this device is then inserted into the skin via a needle. So there's usually a needle that covers this thing, that punctures the skin, and then you retract it with some mechanism that mechanical engineers make. And then that leaves this little flexible sensor that's sitting inside your interstitial fluid. Typically, these devices also have an RF transmitter that basically takes the signal that's being measured here. You have some potentiostat circuitry also in here that allows you to apply voltage between the reference and the working electrode, and that also then measures the current that's being measured between counter and working. And you also have some analog to digital circuitry as well, and that gets transmitted to some other external hub that collects it. This sensor has various layers. It has a biosensing layer, which is basically an enzyme called glucose oxidase. It then has also a glucose limiting membrane, and it also has your electrodes. So this is kind of how it looks. This is a kind of an advertisement for it. It doesn't exactly look like this, but you can get an idea that there should be 3 electrode strips on this device with different geometry, etc. Okay. There's another class of sensors called field effect sensors. So field effect biosensors. And so the way these work is they basically work like transistors, and the kind of the physics behind this basically originates from the fact that if you take a MOSFET, which is basically a transistor, and you compare it to how an electrochemical cell behaves, you actually get very similar behavior. So on the right here, A and B, A shows you a 3-terminal MOSFET, and B shows you a typical electrochemical device. So let me go through that. So for a MOSFET, you usually have a connector for the source, you have a drain, and you have a gate. And in between those terminals, you're going to have a dielectric layer, and that dielectric is basically a semiconductor, right? Because this has a variable amount of conductivity that you can basically tune with by making it N-type or P-type. Then you're going to have charge separation between the source and the drain and the gate. And without going into too much detail, for those of you that didn't take ECE501, you can affect the amount of current going from source to drain by affecting the voltage differences between the gate and the source and the gate and the drain. And so this allows you to do that. And so what makes this kind of nice is that you can use it as amplifiers, you can use them as switches, and that's what makes it very interesting. What's key here for comparing it to an electrochemical cell is that there's charge separation, and applying a voltage at the gate in reference to the drain and the source will allow you to have current from source to drain. Okay, if you look at an electrochemical cell, picture that in between the space here you have an electrolyte, and then you also have the same kind of format. You have a source connector, you have a drain connector, and you have a gate. When you put charge on the gate, that's going to propel like negative ions to be attracted to the positive voltage you're applying at the gate. And with that separation will also create a separation at the other electrode here. And remember that was called the electrical double layer from by putting an electrode in electrolyte solution. So that also creates a charge separation from source drain to gate. And so it basically creates the same kind of scenario as a MOSFET would. Now you're probably wondering, like, why do I care that a MOSFET and an electrochemical cell are essentially the same? Well, so it matters in the sense that if you're able for an electrochemical cell to put on some molecules that will essentially affect the voltage and current characteristics of this device, then you could essentially make a sensor. And this is how they work. If I take the source and drain here and I separate them with some semiconductor, and I get a reference electrode, which is going to be my gate. And so if I can then apply a voltage at my reference electrode and change the ionic composition within the liquid, I can then, in some scenarios, get a current that goes from drain to source, or source to drain, I should say. So let's talk about how that is actually done. So the way this is done is via providing a voltage at the reference electrode for this system. So again, let's say you have a device that has a drain, a source, so two conductors, and in between them you've sandwiched a semiconductor. Let's say in this case it's an N-type conductor. What N-type means is that there's an overabundance of electrons versus holes. And so what happens is when you provide a positive voltage to the reference electrode, which is sitting in the ionic fluid, that's going to attract negative electrons at the positive reference electrode. At the other end, you're going to get now positive charges, which are going to be on the surface of the semiconductor. Well, what that does is it also creates electrons that are then moving or drifting through drain and source. And so then that creates a specific voltage versus current plot. Okay, so that's great. So that's when you positively bias the reference. So you're going to have some current voltage relationship. If you apply a negative bias, you're going to get a different scenario where you're attracting positive ions to that electrode, and then you're going to then have negative ions sitting at the surface of the N-type. Now remember that this is an N-type material, so there's an overabundance of electrons that's going to repel them, so there's going to be no current that's going from drain to source. So that's also going to basically affect the voltage relationship of this thing. So you can actually, plot these two things on a plot, and let's get the one to the very left here. So when it's off, if you were to plot, the gate voltage versus the amount of current you're producing between the drain and source, you're going to initially be, producing no current in here. As you positively bias it, at some point you're going to switch on and create some current through the drain and source, and that just jumps up here, and then you get zero going negative way. So this should be a red line going this way. That's pretty much zero. Okay, so how do you make them into sensors? So you then would basically anything that affects the amount of current that can go through the drain and the source is then going to be able to be sensed by this current voltage relationship on this device. So to do that, you can place some chemicals on the surface of the semiconductor, which then will affect the distribution of ions in your solution. So for instance, let's say you put some enzyme on here. You're gonna, immobilize some enzymes onto this semiconductor here. Anytime some chemical of interest reacts with the enzyme, it will affect the charge distribution here. So let's say, like for instance, that when you apply a positive bias voltage, it actually takes longer for you to produce a current because of the reaction going on here. So let's say, for instance, maybe this produces an electron at this reaction. Then that gets pushed up here, and that will reduce the current that's here because of the charge distribution, which then shifts the voltage current relationship for this device to the left, for instance. So you would be able to see this change in delta V, and then that would be proportional to whatever you're measuring on the N-type semiconductor. You can do the same thing for P-type semiconductors, but you kind of get the idea here. Any reaction, whether it be an antibody connecting to an antigen, whether it be an enzyme reacting with a chemical, whether it be a cell that's sitting on here that's producing again more electrons, anything that affects the ionic composition at the surface of the n-type surface here can potentially affect the current that is produced between drain and source. And so that's the takeaway here. And that's how FET biosensors basically work. Okay. Okay, so actually I've actually reversed this. So I'm actually going to talk about biomechanics next, and we're going to talk about tissue stimulation in 2 weeks, and cardiac pacing and auditory and visual prosthesis. So we'll go over these topics in 2 weeks. Be on the lookout for a video within the next couple of days that talks about biomechanics. So while we are putting all of our lectures online for this week, this does not end the material for this week. We're going to go into biomechanics in the next lecture. So that'll hopefully be posted by Wednesday, if not, definitely by Friday, so you guys can take a look at it on the weekend. Okay, so I'll end it here, and thanks again for watching.